Everybody, welcome to a hopefully brief video on section 9.1. As we discussed in class last time, the point of this section is just to develop some language for the different kinds of pictures you see when you draw slope fields for linear systems. So recall in chapter 7 we saw that the eigenvalues of the corresponding coefficient matrix can determine the shape, the kind of thing you're looking at when you look at the slope field. Sometimes you get a spiral, sometimes you don't, and the eigenvalues determine that kind of behavior. So we are just going to provide language for all of the different, qualitatively different kinds of pictures. So spiral is a technical term, and we'll introduce other technical terms just to give language to what we're looking at. So some preliminary terminology here. So suppose we have a linear system like from chapter 7. We've looked at all sorts of kinds of solutions. Often they have exponentials and trig in them, just like in chapter 3. Just like in chapter 3 or chapter 2, we can talk about equilibria, a solution being in equilibrium if we'd like to. And just like in chapter 2, an equilibrium is just a constant solution. So an equilibrium is a solution that is also constant. So what would that look like? So here we have a 2 by 2 system. So you could think about what if x1 of t were 2 and x2 of t were -1? Those are both constant functions, so when you combine them into a single vector, now bold x is constant. What about a constant vector like this? Is that a solution? I could throw out any constant vector of length 2 and ask, is that an equilibrium or not? And the way you would check is just by plugging it in. So x would go there. The derivative of a constant is 0, so 0 goes there. So this first vector here, if you plug it in for x and do the matrix multiplication, you get 3 times 2, and then -3/2 times -1 gives you a positive 7.5. Well, that's not 0, and neither is the second entry. But if you put a 1 there and a 2 there, 3 times 1 minus 3/2 times 2 gives you a 0, and then the other one's also 0. So 1, 2 is an equilibrium of this system here. Same concept as chapter 2, a constant solution of in this case, system of differential equations. So any system that looks like this has at least one equilibrium. This one here, I showed you one of them, but there are others, perhaps. And so the question is, given any linear system, can you think of one constant vector that always works? And you can pause the video when I ask these questions if you feel like, but if not, just let me point out, if x is the 0 vector, so x is just a column of zeros, well, a times 0 is 0, and the derivative of 0 is 0. So you always get the origin, the 0 vector, as an equilibrium. Other equilibria can be hard to come by a lot of the time because if you want to find equilibria, just like in chapter 2, you take your derivative, set it equal to 0, and then solve. So this here is a bit of linear algebra language. If you don't understand this, it's fine. But basically, if A has an inverse, so the way like 2.5 are inverses, or 5 1/5 are inverses, matrices also have inverses like that sometimes, although not always. But if you can like divide by A, you get this equation. And x is 0 is the only option. Most of our matrices will be invertible in this section. So you're just going to get the single equilibrium at the origin. Also, your book, sometimes I don't know what they're up to. Why introduce extra language? So sometimes they say equilibrium, sometimes they say critical point. They mean the same thing, and for me it's not clear why you need two terms. A reminder about how slope fields work from chapter 7. You can draw that vector field like we've done, and then if you plop your finger down in the slopes app, it'll draw a trajectory for you, which is a representation over time of a single solution to the original system. And so you're watching both x1 of t and x2 of t track over time through that vector field, and that's called a trajectory. So from a trajectory you can get x1 of t and x2 of t individually if you want to, and slopes will show you that in the bottom left corner. The x1, x2 plane itself is called a phase plane, and then if you plop your finger down enough and get a bunch of trajectories, the resulting picture is called a phase portrait. This is all reminders from chapter 7. Okay, so what's the big idea of section 9.1? It's what I already said. The eigenvalues of the coefficient matrix A drive the kind of picture you're looking at. So let's just name those things. So here's an example. This system here, I think we may have looked at it in chapter 7. I guess it doesn't matter. So eigenvalues and eigenvectors. These are the eigenvalues. So they are both real and they are both negative. And then here are the eigenvectors. So it turns out that if your eigenvalues are both real and distinct and negative, your picture will always have the same kind of form. And so let me show you this. I'm not going to hop over to my iPad for the sake of time. So I have these pictures on my local machine. So here's that slope field. It looks like this. So notice the origin is stable, first of all. Like if you tap yourself off the origin, you flow right back. Notice a couple other things though. So it's illustrated in this picture, but let me put up, okay, here are the eigenvectors. 0.371, so what would that look like? Over 0.37 and up 1, so it's an arrow kind of like this. So over, up. And then the other one was negative 1.371. So negative 1.371. I'm going to put both those vectors in just as lines. So check that out. There's one eigenvector line. There's the other one. And notice one of these eigenvector lines is acting kind of like a sink. Like these arrows are trying to get to this eigenvector. And the other eigenvector is not doing that. Right? So there's like a sink eigenvector and the other one's not really a sink. In this picture, it looks like the arrows don't even care really about the other eigenvector. But you see the sort of flow towards one of them. So this is what will happen when you have two distinct real eigenvalues. The eigenvector for the bigger eigenvalue, so negative 2.27 is bigger. The eigenvector associated with that is like a dominant eigenvector, and it draws trajectories to it. And that's what you're seeing in this picture here. So here's the dominant eigenvector here, and trajectories are going to it. And you get something that's called stable, asymptotically stable. So just in case you don't remember how this works, okay, so let's look at this trajectory here. What is x1 doing? So x1 starts positive, right? x1 is positive, and then as you move along this trajectory, right here, x1 becomes 0, x1 is negative, and then turns around. It's still negative, but it's limiting to 0. So if you follow along a path like this trajectory, the x1 curve looks like this. Starts positive, becomes negative, turns around and limits to 0. What about a trajectory like this? x1 is negative, and it stays negative. It just goes up to 0. That's what this path is right here. Okay, anything else that's different? So look at this one. So this trajectory, x1 is negative, becomes positive and then to 0. So you don't see one like this on this picture, but negative, positive, 0, something like that. This trajectory here, say right here, x1 is positive, stays positive but limits to 0. That's something like this. So again, we've seen all of this before. The only new thing I'm really pointing out to you is this eigenvector structure here, which may or may not be important, but this kind of looking at trajectories and then from that getting a graph of x1 or x2, we've looked at that, and slopes will do it for you. Okay, but all of that to say, this language here, that describes the kinds of pictures you get when you have two real distinct eigenvalues, both negative. You get an asymptotically stable node. You get a dominant eigenvector that draws arrows to it and then funnels them to the origin. Okay, let me now just give a brief bit of terminology about stability. So back in chapter 2, we just said stable or unstable. And technically, the book said asymptotically stable, but it said asymptotically all the time, so I just dropped it. But now asymptotically actually makes a difference, and we'll talk about why in a second. So asymptotically stable means your equilibrium acts like a sink. It will draw things to it. Unstable means the opposite, acts like a source. So if I knock you off the origin, you flow away from it. So it's like a repellent or a repeller. I don't know what the right noun is. And then you're stable if actually neither of those things happen. So now if I remove the adverb asymptotically, for an equilibrium to be stable now, what it means is it's not a sink or a source. So it doesn't draw things to it or repel things away. Things orbit around it. So think about orbiting around the origin the way the moon orbits the Earth. So the moon doesn't crash into the Earth. hopefully. The moon also doesn't shoot away from the Earth. It's just kind of stably respecting its distance from the Earth. That's what a stable equilibrium would look like. So I'll show you an example like that in a second. Okay, so here's another example. So 3, -2, 2, -2. Its eigenvalues are real and different, but notice they have opposite sign, one positive and one negative. So it turns out when you have real eigenvalues but they're of opposite sign, you will get a much different picture than what we saw a second ago with the node. So let me show you that. Get this all out. Okay. So look at that. So now see, the origin is not stable. If I knock you off the origin, off you go. You're not coming back to the origin. And now let me show you the eigenvector lines. So eigenvectors are 2, 1, and 1, 2. So 2, 1 is like over here, 2, 1, and 1, 2. So the vectors are pretty close to each other. So there you go. But notice the eigenvector lines carve the plane up into sort of 4 parts. So in this part, this eigenvector line kind of shoots arrows away, and then they flow to the other eigenvector line. And same thing down here. The arrows are moving away from the line, and then up to this one. And same thing here. So you get this sort of curvature, right? Four pieces of the plane, each of which is curving towards one of the eigenvector lines. And this eigenvector here, the one that's drawing things to it, is the eigenvector corresponding to the number 2. 2 is bigger than -1. So whenever you have real eigenvalues that are different, the bigger eigenvalue, its eigenvector will be dominant and draw things to it. And the other eigenvector line will sort of be a repellent. It'll shoot things away from it. This is called an unstable saddle. So the origin is an unstable saddle point in this example. Okay. So all of that to say, I could just keep showing you pictures, and I will very quickly here. But at some point, there's just diminishing returns, analyzing everything. Here's a summary of what happens. So if you get 2 real eigenvalues, and one is positive and one's negative, you get an unstable saddle point, this table is saying. If you get 2 distinct real eigenvalues, and they're both negative, you get an asymptotically stable node, as we just saw. There's all sorts of other things that could happen, like your eigenvalues could both be real and negative but the same. Then you get what's called an improper node that's still stable. You could, of course, get complex eigenvalues, and in which case you would get spirals. Okay, so the main takeaway of this section is this table. You don't have to memorize this table. So on your next exam, this table will be given to you, but you got to know what it's saying. So you got to be like, oh yeah, R1 and R2 are distinct real eigenvalues. These are complex eigenvalues. Okay, let me just show you some more pictures real quick. If you want to see the actual system I'm plotting, I'm just going to plot these 6 for you real quick so you can see the different kinds of pictures you can get. There are 5 here. There's a 6th one here. This last one doesn't have asymptotically as an adverb, so this is the moon orbiting the Earth kind of thing. So let me just march through and show you an unstable node, improper node, and so on. So get rid of this. Okay, this is an unstable node. I think it says, yeah. So here are the 2 eigenvector lines. So notice, basically the stable node picture, the arrows have been reversed. So if I reverse these arrows, what it looks like is happening is this eigenvector line is drawing things to it if the arrows were reversed. So if the arrows were reversed, you have a dominant eigenvector shooting arrows down to the origin. That's a stable node picture. So an unstable node, it just reverses that picture. So now the dominant eigenvector is acting like a source. It's shooting things away from it. And now notice the arrows are kind of going to the less dominant eigenvector, but they're going away from the origin. So an unstable node is just like a stable node with the dynamics completely reversed. You reverse the arrowheads and you get like the opposite picture. There's an unstable node. Okay, now what is this? 2. So here there are 2 positive real equal, so they're not really equal. They are real and also equal eigenvalues. This is called an improper node. It's unstable, as you can see. If I knock you off the origin, off you go. It looks just like an unstable node, like the adjective improper seems like it doesn't really matter. All that it's saying here is that there is no other eigenvector line. So here, there aren't two eigenvector lines to carve things up because you only have one eigenvalue. But for our purposes, this looks just like an unstable node. I'm just including it because your book includes it. This is a stable improper node. So again, there's not another eigenvector line happening here. There's just one eigenvector line that's drawing things to the origin. So that's a stable improper node. And then finally, we get to some spirals, I think. So we finally get some complex eigenvalues. So, okay, so now I'm going to graph this one. So these eigenvalues will be complex with positive real part. That gives you an unstable spiral. So if I start here, say, okay, watch the arrows go. So I'm not in slopes, so I can't make the trajectories. But you see, you spiral away from the origin. And so slopes will show you that, show you going away from the origin. If I start here, up, and then my distance from the origin keeps growing as I follow the arrows. Now, if I have complex eigenvalues but with negative real part, I get the same picture but in reverse. So this is now spiraling me to the origin. We already looked at this the other day. The last thing I want to show you is this system here. There are complex eigenvalues, but they're purely imaginary. There's no real part. Then you get what's called a stable center. Now, if I were you, I would also graph this in slopes, so you can ask slopes to give you a trajectory. But if I put my mouse here and I follow the arrows, if I follow them and I'm precise about it, what will happen is I will end up back where I started. So I'm not being thrown away from the origin, like the unstable spiral. I'm not being drawn toward the origin, like the stable spiral. I'm just in an elliptical orbit around the origin, like that. If I follow the arrows precisely, I will return to my start point. So again, if I were you, I would ask slopes to graph this for you, to make a slope field out of this one, and have it plot these elliptical trajectories for you. And then if you watch the x1 graph go, or the x2 graph, it'll graph both of them for you. Let me come back up here. You're going to see just a pure sine wave that neither explodes nor dies down. So you just see up, down, but no growth or decline in the amplitude. Because here, if you think about what x1 is doing, so if I start here, x1 is negative, then it becomes positive. Now it's 0. Now it's that same negative value I started with, and then it just repeats. So again, the amplitude neither grows nor declines, as opposed to something like this. So here, if I follow the arrows, it's like up, down, but the amplitude is dying down because I'm spiraling towards 0. Or here, like in slopes, if I start here and I follow the arrows, my amplitude is growing because I have growing exponentials attached to my trig. But with purely imaginary eigenvalues, and that's the case I'm in, purely imaginary eigenvalues, 0 real part. Remember, the exponential functions come from the real part. So if there's 0 real part, that means the exponentials are gone. So your answer just has trig in it. And trig neither dies down nor explodes on its own. So that's how you can get a stable center. Okay, so the punchline of this section is this table, which you don't have to have memorized, but you have to know how to use. There's language involved with any kind of picture you can get. I've shown you several pictures. All of these pictures are in Brightspace, by the way. If you go to the Chapter 9 module, all the pictures are there and they're labeled by their name. So if you want to, if you're like, oh wait, what was an unstable saddle? There's a PNG file on Brightspace called unstable saddle, and then you can open it and see what it looks like. Okay, so that's all section 9.1 is, just this language. So we pick up on Monday with section 9.3, which has a lot more meat to it than this.